Here we have a video over solving trigonometric equations. So first I want to start off by posing a question. When does the cosine equal 1/2, but only on the interval between 0 and 2 pi? So what I want to think about first is, let's do some visual thinking. Let's take the left side of this equation, cosine, and make it its own equation, and take the right side of the equal sign, 1/2, and make it another equation. And we're going to plot this on the xy coordinate plane. So instead of using our typical number line for the x-axis, we're going to use all the radian values that were on our unit circle, and we're going to plot what cosine would look like. And here's the cosine graph starting up at 1 on the y-axis and using the quadrant angles at pi over 2, pi, 3 pi over 2, and 2 pi to plot them. And then again, you notice that I only did this over 0 to 2 pi since our interval is only concerned about those particular x values. Graphing then the 1/2, y equals 1/2, our job is to then, like in systems of equations, where do these graphs intersect? Well, of course you can see this graph, or these two graphs intersect twice. And if we take those two intersection points and go straight down to the x-axis, we see there is one solution at the radian pi over 3. The next solution goes down to 5 pi over 3. So in our equation here, we would say that our solutions are pi over 3 and 5 pi over 3, and these are the only two solutions that go to this particular trig equations. But what happens when we change the interval? What if we're not concerned about just 0 to 2 pi? What if we say, what are the solutions from the interval of -infinity to +infinity? What are all the real solutions to a trig equation? Well, what that tells us then is we need to remember some background information or some previous knowledge about these trig functions, like what are the periods of all the trig functions? The period for your trig functions like sine, cosine, cosecant, and secant, we had 2 pi, and for tangent and cotangent, we had a period of pi. Now you may notice next to the pi and the 2 pi, we have this variable n, and what n stands for is this is an integer. How many times do we want to do the period? Do we want to go one revolution around the unit circle? Do we want to do a couple of revolutions? Do we want to go backwards into the negative radians? Whatever it is that we want to do. So what this is telling us is this covers all the coterminal angles that are the coterminal angles to that original solution that we have. So if we want to go back to our equation, cosine of x equal to 1/2 over the interval -infinity to +infinity, what we have to say then is, what was our original solution? It was pi over 3. Cosine has a period of 2 pi, so we have to add 2 pi to it with that multiple of n. So all of the solutions for this trig function is pi over 3 plus 2 pi n, and then our other original solution was 5 pi over 3 plus the period of 2 pi n. And that's how we do the trig equations over an infinite interval. Okay. We can solve trig equations several ways. We can do isolating the expression, much like we used to isolate the variable in algebra. We can do factoring by, we've got different methods of factoring. We have the greatest common factor. We have quadratics, where we could use things like difference of squares. We could use the AC method of factoring. We can do factor by grouping. And we could also use the identities that we've learned in this class, such as like the reciprocal forms, the quotient forms, Pythagorean identities, sums and difference formulas, and many others. And for this video, what I planned on focusing on are the first two bullet points. We're going to do the isolating the expression, and we're going to do some factoring. So let's get into our first example. So isolating the expression, we're going to solve for the values of our variable over whatever the given interval is that the problem tells us. So first example, we have 5 sine of x plus root 2, and that's equal to 3 sine of x. I'm going to use that sine of x and pretend that that is my variable. So I want to get those like terms to the same side of the equal sign. And if you notice again, the interval would be given to you off to this. What does -infinity to +infinity mean? This means infinite trips around the unit circle. So again, I take my like term. I'm going to take that 3 sine of x, subtract it over to the left side, and do my like terms. 5 minus 3 sine, that would be my new sign. I'm also going to take that root 2, subtract it away from the left side, and bring that over to the right side, and simplify my equation. This gives us 2 sine of x is equal to -root 2. Divide both sides by the 2. And my equation now says sine of x is equal to negative root 2 over 2. And again, I'm a very visual person. I'm going to pull back up our unit circle that we've learned in previous lessons. If you remember that the sine is the y value of the ordered pair, my job is to go around this unit circle and figure out where are the y values equal to negative root 2 over 2. Well, starting at 0, if I travel around, I will get to that particular radian right here. There's my first y value that has negative root 2 over 2. So our first solution will be 5 pi over 4. But you will also notice that this is not the only radian that has a negative root 2 over 2 as the y value. There's also one at 7 pi over 4. So there are two solutions within one trip around that unit circle, like so. So there's my 5 pi over 4. But since we're on that infinite interval from negative infinity to positive infinity, we have to add in that period unit. So we have to put plus 2 pi in afterwards. The second solution we said was 7 pi over 4. And again, we're on the infinite interval, so we'll add in that plus 2 pi in. And this is what we'll say our solutions are for this particular trig equation. So that's isolating the expression. Some more isolating the expression. What about 3 tangent of theta plus 2 root 3 equal to 8 root 3 minus 3 times the tangent of theta on our infinite interval from negative infinity to positive infinity. Need to get our like terms together. So I will add 3 tangent from the right side over to the left. And I will then bring the 2 root 3 by subtracting it over from the left side to the right side. So cleaning this up will give us 6 tangent. And the 8 root 3, take away 2 root 3s, that would leave us with 6 root 3s. Then from there, we'll divide both sides by 6. And we are going to look for solutions that have tangent values of root 3. I'm going to go back up one more time to our unit circle. Feel free to take a screenshot of this unit circle so you can refer back to these solutions. All the solutions that I have in pink are the tangent values at the given radians. So the first one that we have, a positive root 3, we look up here, there's positive root 3. So our first solution is going to be pi over 3. I keep traveling around, and the next positive root 3 solution that I have is down here. So we're going to use 4 pi over 3 as the solution. And how do we write that solution? The first one that we ran into was pi over 3, infinite interval. So we have to add in the period for tangent, and this time it is pi. So we have to put pi in. And our other solution, backtrack on that. Now you may notice that I did not write 4 pi over 3, and the reason being is that if I were to add one multiple, say I put a 1 here for the n, when you add pi over 3 to pi, you end up getting 4 pi over 3. So there's really no reason to write that 4 pi over 3 since it is included in this particular solution. All right, so moving on to example 3. How about the secant of alpha minus 6 divided by 4 equal to negative 1? Again, we're going to look for all these solutions within this real numbers. Well, I'm sure you're a lot like me. We don't like to deal with fractions, so if we're going to divide everything by 4, why not go ahead and multiply everything by 4? That would cancel out the 4 on the left side and leave us with the secant of alpha minus 6 equal to negative 4. We want to isolate our trig function, so add the 6 over, and that gives us secant is equal to 2. Now our unit circle, we don't have all the cosecant values, the secant values, and the cotangent values written down, but I do know that secant is the reciprocal trig function of cosine. So if I can reciprocate, meaning flip the fraction of 2, then I would know the cosine value that I'm looking for. So cosine would have to be 1/2, and then I would go back to my unit circle and look for what are all the x values of the ordered pairs that are positive 1/2. And those radians will give us 1 as pi over 3, and that is with the plus 2 pi in for its period. And the other solution is 5 pi over 3 plus the 2 pi in for its period. How about dealing with some type of quadratic involved? All right, and you may also know that our interval has changed now. Now we're only going from pi to 3 pi over 2. Now, if you, again, look at your unit circle, this is just quadrant 3. So there may be solutions that are within the entire unit circle, but I'm only concerned about the solutions for this sine value that's in the third quadrant. So let's isolate sine squared. Let's subtract 8 over, and then divide by 4. Now we learned in algebra that we can get rid of a second power by square rooting both sides. And when I square root both sides, please don't forget to put that plus minus symbol in there. I've also simplified my square root of the 3 over 4 that we can square root 3. We don't have a perfect square for 3, but on the bottom 4 is a perfect square, so we do have the square root of 4, which is 2. And originally we were thinking, well, what are the solutions that have a positive root 3 over 2 and a negative root 3 over 2? But again, we're in the third quadrant, and in all the sign values, all the y values in the third quadrant are negative. So that leads us to ask, well, when is the y value of the ordered pair going to be negative root 3 over 2? And that, again, if we look at our unit circle, is going to be at 4 pi over 3. And this, again, would be the only solution that is in that third quadrant within that little interval there. We are not going to use any of the other ones. Moving on, how about factoring? The first example that we're going to look at here is going to involve our idea of using difference of squares. And I know that this is the difference of squares because, one, there is a difference between my terms. The second is the 4 and the 1. Those are perfect squared numbers. Look, if you look at our interval, we go from 0 to 2 pi. Now, these are really nice intervals here because this is just one trip around the circle. We don't have to worry about adding in all those coterminal angles. So, what's the difference of squares? Let me remind you that a squared minus b squared in its factored form is a plus b times a minus b. And the easy way for me to do the difference of squares is to draw 2 blank parentheses and ask myself the question that what number would I have to square or raise to the second power that would get me back to 4? That number would be 2. And what would I have to raise to the second power to get sine squared? That would be sine. And in the second parenthesis, what do I have to raise to the second power to get positive 1? That would be 1 itself. And reason being, what I have in red, it would be my a. What I have in blue would be the b. And I get to substitute those two pieces into the factored form. So this would factor into 2 sine plus 1 times 2 sine minus 1. And then we have our lovely zero product property that if I have the product of two things is equal to 0, then one or the other would have to equal 0. We're going to be a little picky. We're going to set each factor equal to 0 and solve them. So I'm going to start with the one on the left. 2 sine plus 1. Go ahead and subtract the 1 over. Divide by 2. And I go to my unit circle. Figure out where are all the y values of those ordered pairs. Negative 1/2. Well, for this particular factor, that would be at 7 pi over 6 and 11 pi over 6. Go over to 2 sine minus 1 and solve that equation. Add 1 over, divide by the 2. Now you have to ask yourself, where are all the y values equal to positive 1/2? So that's going to occur at pi over 6 and 5 pi over 6. So there's actually 4 solutions to this equation here. And we write them all out. We got pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Well, that's a difference of squares factoring method, but what other factoring methods do we have? What about greatest common factor? Let's look at these solutions within our interval from pi to 3 pi over 2. Pi to 3 pi over 2, again, that is the third quadrant. Let's see. Well, in our terms here, notice that this term has tangent in it, and this term also has tangent in it. So we would factor out our greatest common factor of tangent, and I used the distributive property backwards to help me fill in the missing factor. Tangent times something gets you back to 3 tangent squared. That would be 3 tangent. And tangent times something is going to be negative root 3 tangent, and that is negative root 3. And just like we did in the previous problem, once we get something factored, we take each factor and set them equal to 0. So that means tangent gets set equal to 0, and 3 tangent minus root 3 will get set equal to 0. Now this one is already set for us to solve, so you would go to your unit circle, look in that third quadrant, and see, do I have a tangent value within that third quadrant that has a tangent value of 0? And you do in fact have pi. Over to the 3 tangent minus root 3. We would add our root 3 over, divide by 3, and look to see, do I have a tangent value that has root 3 over 3 in that third quadrant? And once again, you do. This would be at 7 pi over 6. So there are 2 solutions to this trig equation, which are pi and 7 pi over 6. Okay, 2 more examples to look through. We have sine squared plus 5 equal to 7 minus sine. And we're going to do this between pi over 2 to pi, which if you look at pi over 2 to pi, that would be in the second quadrant. One thing I am going to do is I want to bring everything over to one side of the equal sign, and this looks like it's in a quadratic form, so I'm going to have to factor this using the AC method. Now, what is that AC method? Let me remind you that we're going to take the quadratic leading coefficient times it by the constant. Your job is to look for two numbers that multiply to get the product of A and C, but if you add those two numbers together, you're going to get the middle number of B. So what's that look like? We got 1 times negative 2. What two numbers do I need to use that multiply to give me negative 2? But if you add those two numbers, you're going to get positive 1. Those two numbers are going to be 2 and negative 1. And what I do with these two numbers is I replace the middle. So I'm going to take 2 and that negative 1, and I'm going to break apart this, and I'm going to have 4 terms now that looks like such. So anytime I have 4 terms, I can always use grouping. So I'm going to look here and say, well, what do I have in common between sine squared and sine? That greatest common factor would be sine itself. What would I have to fill in with my parentheses here? Well, sine times sine will give you back sine squared. And sine times something will get you back to 2 sine. That is a positive 2. Now, one of the great things about grouping is that whatever this parenthesis is going to be will be the same parenthesis when you do grouping for the last 2 terms. So I will always write a copy of that and ask myself, what number would I have to put here that if I were to distribute it back in, I would get negative sine back? Well, that number is negative 1. And you notice that I put the sine and the negative 1 in green because those eventually will get grouped together as a factor, and the sine and plus 2 is the other factor. Okay, so now we have this quadratic form factored apart. Our job now is to take each factor and set them equal to 0 and solve. So starting with the green one, we're going to add 1 over, go to my unit circle, look within that second quadrant and see, do I have any sine values that are positive 1? I do, and that one is at pi over 2. On the second factor, sine plus 2, we'll subtract the 2 over, but this poses a problem. You may look at your unit circle and see, well, there are no y values of ordered pairs that have negative 2. And that's because the range of sine and cosine is always going to be between negative 1 and 1, including negative 1 and 1. So if you get anything bigger than 1 or anything less than negative 1, there isn't a solution that exists for that. So there isn't one that exists for this factor. So therefore, the only solution to this problem is going to be pi over 2. All right, last example. We've got 4 terms here, and anytime I see an even number of terms, my first go-to method would be to use grouping. So I look at the first 2 terms, take out its common factor, which would be a tangent squared. When you take the tangent squared out, you're going to be left with the tangent plus 1. So therefore, since tangent plus 1 is that factor, my second factor must also be tangent plus 1 for this. What do you have to put in this space here that to distribute back in, you would get negative 3 tangent? That number is going to be a negative 3. So the factored form now is tangent squared minus 3 times tangent plus 1. We want to take each of our factors and set them equal to 0 and solve. So starting with tangent squared minus 3, add the 3 over. Square root both sides. Anytime we square root, we've got to put the plus or minus in front of the root. So what tangent values or what radians do we have? A positive root 3 and a negative root 3 over that interval of 0 to pi. Now that interval there would be the first and the second quadrant. We get at pi over 3 and 2 pi over 3. Going to our other factor, we want to subtract 1 over. And again, go back to our first quadrant and second quadrant and see, do I have any radians that have a tangent value of negative 1? And that would be at 3 pi over 4. So there are 3 solutions to this particular trig function, and those are pi over 3, 2 pi over 3, and 3 pi over 4. So there you have some factoring methods and isolating the expression to solve for trig equations.